dear students, welcome to my this topic on crystal field splitting energy or crystal field stabilization energy. You already observed how the octahedral complex d orbital splitting, how the tetrahedral complex d orbital splitting takes place because of the approach of ligand towards the metal ion in the coordination complexes in the previous class. So that is actually happening only because of the magnitude of the charge present on the ligand when it is approaching the central metal ion. So metal ion also exhibits charge. Ligand also considers point charges according to our crystal field theory. So because of these all aspects, now we are going to talk about crystal field splitting energy or crystal field stabilization energy. That will give us an idea about why the ligands are called as weak ligands, why the ligands are called as strong ligands. Very simple. In this, the ligands which cause a small degree of crystal field splitting, that means crystal field splitting is nothing but small degree, means whenever crystal field splitting is there, small degree of crystal field splitting, they are called as weak field ligands. Weak field ligands. So what do you mean by this weak field ligand? Ask anybody. Weak field ligand is nothing but the ligand which cause a small degree of crystal field splitting, which is called as weak field ligand. Examples we have I minus, Br minus, Cl minus, etc. will come. Whereas ligands which cause high degree of, ligands which cause high degree of means large degree, high value of crystal field splitting, they are called as strong field ligands. Strong field ligands. In our discussion of examples present in our syllabi, we can consider NH3, Cn minus, CO, or these examples of this strong field ligands in a systematic arrangement of increasing order of field strengths given to us according to the crystal field theory, which we can also call it as spectrochemical series. From that, we can divide these ligands in these categories called as crystal field splitting energy caused by the ligands onto the central metal ion. Means ligands field splitting also is the another word we can use in this junction. Okay. Hope you observed the last session also between the octahedral complex and the tetrahedral complex there exists a crystal field splitting relation. The delta whatever we will use, that is crystal field splitting energy, and that energy will be noticed delta T for the tetrahedral complexes and delta naught for the octahedral complexes. The relation with the mathematical formula which we have given is delta T is equals to 4 by 9 delta naught, which indicates delta naught is greater than delta T always. That means in the tetrahedral complexes, the crystal field splitting energy is lower than the octahedral complexes. The reason is nothing but in tetrahedral complexes, the ligands are actually, most of the ligands are said to be weak field ligands. So, most of our discussion will be carried in the octahedral complexes, and in the octahedral complexes we have d orbital splitting, we called as the two groups EG and T2G, as I said earlier in the CFT, crystal field theory, in the previous sessions. Okay, now we are going to talk about the arrangement of the electronic arrangement of the metal ions in the octahedral complexes. Electronic arrangement. Electronic arrangement of metal ion in octahedral complexes. So let us just briefly observe what is the electronic arrangement in the octahedral complexes. If you take octahedral complexes, we have 5 d orbitals, how they split and all we observed. The 5 d orbitals in the octahedral complexes are said to be split into two groups. One is T2Z, another one is EG group. In EG group we have dx square minus y square dz square orbitals. T2G group we have dxy, dyz, dzx orbitals are present. Suppose if a metal is having configurations like D1, D2, D3 configurations are there. D1 configuration is there, means definitely the electron will enter in the T2G orbital like this. So there is no electron present in the EG orbital in the D1 configuration. While that of D2 configuration also, then we have electrons existence will be in the T2G. So if you take D3 configuration, all the 3 electrons will be present in the T2G orbitals after the arrangement when the ligands are approaching the central metal. This all we are following according to Hund's rule of the electronic configurations rules. Maximum multiplicity, Hund's rule of maximum multiplicity is the rule we will use. Coming to the another point here, we have two types of options are there when we have a D4 configuration is considered in the complex compounds. Two types of options. D4 configuration will give clarity about the ligand's behavior, whether ligand is a weak field ligand or strong field ligand. Suppose if you take T2Z, EG, T2Z like this, if the D4 configuration is giving 4 unpaired electrons like this, 4 unpaired electrons, definitely this is said to be against the strength of the ligand, means ligand field strength. Ligand causes weak field, that's why that ligands are called weak field ligands electronic configuration. So D4 configuration you can write for the octahedral complexes, that is EG1, T2G3. Whereas strong field ligands are there, means definitely for this strong field ligands SFL, weak field ligands WFL is the shortcut I am using. The D4 configuration we will use, and pairing up of electrons definitely takes place in this case as the ligand is strong field ligand, and where the pairing energy changes, means pairing energy is smaller than the crystal field energy, whereas delta naught is greater than P. Here delta naught is less than P. P stands for pairing energy in this category. So pairing energy is smaller, pairing energy is greater. Pairing energy is smaller means strong field ligand. Pairing energy is greater means that is weak field ligand. Understand? So this is what the difference between strong field ligand and weak field ligand in the crystal field splitting energy concept. We will have a next discussion about crystal field splitting energy calculation portion as well as the different ideas in the octahedral and tetrahedral in the next small video. Okay, until have a nice day. Thank you.